without further ado, my name is Chalaya, if you didn't know me. I work on academic collaboration. So I am really lucky to host people like Soumen for Tech Talks here. I don't need to read out Professor Soumen's bio. Many of you may be aware of his work. Some things which I want to highlight, at least from whatever I observed him for over the last few years, his passion for teaching. Right? I had listened to him in an half-a-day summer school in Yahoo in 2011. And also at the same time, the way he has articulated his depth in research from publications, you name some of the top-tier conferences like WWW, CIR, KDD, EMNLP. He's everywhere. And just now you're sharing an anecdote, he's going to give a full-day lecture at CIR. And that opportunity is huge. But somebody like him, stretching out and giving those, we are all very fortunate that way. Third part, which is more important for a company like Flipkart, his industrial experience. He cut his teeth at IBM Almaden. Another person I respect, Prabhakar Raghavan, someone worked with himself. And then now, after all these years, he went and spent a couple of years at Google. So that kind of breadth and depth, I think it's very important for Flipkart, and he already had some good conversations with some other teams here. I think you will really like his talk and make the most of this opportunity. So Soumen, thanks a lot.
Thank you. Can you hear me clearly? Okay. So I'm actually humbled talking about question answering in a commercial organization which manages millions and millions of queries per day. So I'm not sure if I'm carrying coal to Newcastle or saying something. It was the summer of 1955, and half of you groan and say, "Oh, we heard this 40 times already, right?" So let's hope not too much of that happens. So today I'm going to talk about question answering in the context of not e-commerce, but the World Wide Web corpus and knowledge graphs like Freebase or Wikipedia. The questions of structure, and in fact, ever since the major search companies started getting into knowledge graphs and integrating knowledge graphs into their query systems, the structural complexity of queries has improved or increased steadily. And in 2012, Microsoft Bing published this paper where they broke down queries according to some basic idea of structural complexity. At least 57% of web search queries, even in 2012, had some notion of entity or a target type or category. So you might ask Michael Jordan, and those for our purposes is a little less interesting. Michael Jordan may be ambiguous, and you may actually be looking for the less popular Berkeley professor. And then you might want to refine your query and say Michael Jordan, Berkeley, to ask about an entity which is not the majority entity on the web. Or you might want to say Michael Jordan height, in which case you're looking for the height of Michael Jordan. That's a little different from Michael Jordan Berkeley. In other cases, you might ask, like, which college did Michael Jordan go to? In which case, it's a single relation hop query. So if you say, which scientist played the violin? Violin is an instantiated and grounded entity in the query. Played by is a clue of the relationship which connects it to your unknown entity, E2, that you're trying to find out. And you're hinting that whatever you're looking for has type scientist. So structurally, these two queries are identical. Dolly cloned at which institute? Violin played by which scientist or scientists? Right? Some of these have unique answers, some of these don't. So that's an interesting detail. And a slightly more complicated query template is who acted as Bhaskar in the movie Anand, in which case there are two E1s actually. So you're talking about both a character and a movie. And there's a role relationship. It's like a three-array relation, which is implemented as a star graph in standard knowledge graphs. Once again, you're looking for E2 who acted in that role. And just the fact that who acted, this part of the query hints that your T2, the type of the target, is an actor. So we'll talk about queries roughly of these levels of complexity in today's talk. In the early parts of the talk, we will try to segment and annotate the query. We'll try to understand that this who acted is a hint of T2, whereas Bhaskar and Anand are grounded entities, and the likely relation involved is movie actor role. Okay. And late in the talk, we will see that hard segmentations and annotations of the query are not as successful as doing a soft detection of type and relation clues from the query using neural mechanisms. When do these queries work well already? So very smart people are working on these problems, and search engines evolve and improve steadily. As a result, if you ask things like Bruce Willis movies, the answers are great. They're sorted by popularity. If you change the query slightly to funny Bruce Willis movies, the ranking changes instantly because you already have structured metadata. So from sorting by popularity, you're now selecting on a genre of a movie and things work out fine. When you move outside these verticals, the story is not as clear. If you ask which phones have unsafe batteries, apparently that is not the dominant way in which people ask a query like this. And a standard search engine does not do a call out to a specific entity. Although most of us, when talking to friends, they'll say, oh, don't buy a Galaxy Note 7 because it will blow up or something, right? So let's change the query a little bit and say exploding phones. This is apparently a more natural way of representing the problem, although in reality, the phone doesn't really explode. It just melts and burns, right? So that does much better, partly because of click-through signals in ranking. So how Samsung moved beyond its exploding phones from Washington Post. And yet, there is no direct call-out of the specific phone model. The specific phone model or models that are troublemakers are well-established entities in Wikipedia and Freeways. In spite of that, those are not featured. Now let's take the query suggestion, which phone was exploding. And now we do this, and now things get even a little better. Inside Samsung's exploding phone, Samsung Galaxy Note, right? And yet, the highlights here are highlights depending on the query. The highlights are not depending on the answer type that you're looking for. In reality, all I want is this specific brand and perhaps a gruesome picture like this, saying don't buy that phone, right? It's a standard entity. So this is still yet to happen. This doesn't happen with enough reliability today. Here's another query which is even more weird. So if you say Dolly was cloned where, and there's basically just organic output without any callouts on the place where Dolly was cloned. Now, where is a little ambiguous. It could be a city, a state, a country, a planet, right? So you can qualify it and say Dolly was cloned which organization, or in which organization. Doesn't matter, you just get the Wikipedia page for Dolly the sheep. And sure, you can scan the page and find your answer in there, but it's not as convenient a call out as if you got the institute name. So you change the query to Dolly was cloned which institute. And this time you strike gold, Roslin Institute in Scotland. But this is a kind of sensitivity which we don't want. I mean, I think the intent in all three queries were good enough, and the intent in the last two queries were excellent. It's very easy to infer. And still the callouts didn't happen for any of them. And in fact, Roslin wasn't even highlighted. Institute just literally matched the query. So why is this happening? In summary, I want to avoid this brittleness. I want to get callouts which are accurate across a spectrum of entities, types, and relationships. I want to get reliable callouts across a spectrum of query expressiveness. If a human thinks that which organization and which institute are similar enough, I want the query system to understand it as similar enough. So in the words of Fernando Pereira, instead of falling off the structure cliff because of brittle matching algorithms, we want to gently slide down the structure ramp. So whenever there is structure, we want to exploit it. But if there is no structure, we shouldn't fall off and just do organic responses like that. So for the purposes of this talk, a knowledge graph is a type hierarchy like person, physicist, instances of types like book has 3 instances in this picture. Those books may have different names, but the books are abstract things. They have aliases. Similarly, P number 22 is Albert Einstein, a particular physicist. They're also bound by various relationships. Persons author books, and people are born in places, and so on. So that's the knowledge graph for the rest of the talk. So the KG is, of course, hugely useful, but its coverage is poor. And throughout this talk and our work, we'll see how integrating information from the structured low coverage KG and an unstructured high coverage corpus can be integrated into providing excellent ranking. So consider this query, losing team baseball World Series 1998. The query as presented has all the words colored green. Suppose I tell you that some segment here is actually a hint of the target type, and the rest of the query is meant only for selecting little passages from a corpus. So we call them selectors. Can we automatically separate or segment the query into these 2 parts? Suppose by mistake, we think that World Series is the hint at the target type. If we try to match it to a large type catalog such as Wikipedia or Freebase, there will always be matches. In fact, one thing I learned while poking around in Freebase is that any 3 to 4 word English phrase is either the name of a rock band or it's something else. Okay. So you'll always match something. For example, you'll match World Series hockey teams. And the score isn't bad. I mean, World Series is a high signal phrase. But that would lead you into like hockey, which has nothing to do with baseball, and that's partly why you should arrest that match. And instead, the correct choice would be that team and baseball are the hints toward the target type T2. And the rest of the query is the part that matches the corpus snippets. So if we choose the correct type hint, we can then lead on to the correct type, Major League Baseball teams, of which the San Diego Padres is an instance. There are other instances, but this particular instance is mentioned in maybe thousands of pages on the web, talking about them losing in 1984 and 98 in the World Series. And those green words are very special because they link back to the query. Right? So this is an example where different parts of the query have different roles to play. And depending on the role, they are matched to the knowledge graph or the corpus in very heterogeneous ways. They're not matched in the same way with the same scoring function. The scoring functions are different. And to decide that San Diego Padres is a good answer, the correct answer to this query, we have to take into account all these edges through the 3 artifacts, the query, the KG, and the corpus. So we need to discover the query word roles, and this is nothing new to search companies and Flipkart in particular. And for now, we'll start with 2 roles. Either the target type, marked in red, or things that match the corpus in green. Both matches will be soft and scored continuously. So how do we solve this problem? In information retrieval, a standard trick in scoring a document is to not think of going from the query to the document, but thinking of going from the document to the query. You start from the document and you somehow abstract some parts of it away, and you're left with the query with a certain score. And that's used to characterize ranking. We'll do the same thing here, except generating the query is now more complicated because you have to generate words of 2 colors. So here's a generative story. We don't directly use this story, but it's a good guideline for developing more complicated models. First, there is a type description language model. When you ask about a scientist who played a violin, scientist is an abstract notion in your mind. You're transcribing it to a string SCIE, etc. So that's that model, which transcribes an abstract type in your mind into a string. For every query in my training set, there is a bunch of candidate entities. For each entity, there is a language model which describes that entity. So which scientist played the violin? The candidates would include all scientists in your knowledge graph. And Einstein would be described somewhat differently from, say, Jagadish Bose. So each entity has a different language model describing them. Einstein played the violin. Maybe Niels Bohr never played a violin. So that's how their language models differ. And that's why there are EQ plates stacked. For every scientist, I have a language model describing them. Now, as I said, we are going to work in the opposite direction. We're going to start at the answer Einstein and work our way toward generating the query. Yes. And, okay, so we choose the entity Einstein. And now we have to start asking about Einstein using which scientist played the violin. That's a selection. Einstein actually belongs to many types, including, sentient being, scientist, physicist, biped mammal, right? But no one asks a question for Einstein asking which biped mammal played the violin. So there is a certain bias on how I select a type given the entity. That is represented by this distribution. So I choose an entity secretly, then I choose the type. And now I start generating the query word by word. For each word, I toss a coin Z. If the coin turns out heads, I ask which scientist. If the coin turns out tails, I say played the violin. So that information comes either from this side or from that side. So which scientist played the violin? Yes? Slightly closer? Okay. Okay. So this is the whole story of how the query is generated. It's a very simple story. And writing it out in formulas, it looks like that. Given the entity, I choose the type. I choose the segmentation of the query, Z itself. The whole stack of Z's is this vector. Given Z, I extract the type hints, and that has to agree well with the specific T I chose. And finally, whatever else remains of the query are the selectors. And in the corpus, there had better be a whole bunch of passages where the selectors are co-occurring with the entity. That would increase the overall score of the entity given the query. So the overall picture is like this. There are two parts scoring, one going through the knowledge graph, one going directly. And the query is segmented into two parts, disjointly. And this is just a generative story, but that leads to standard discriminative feature vectors and feature-based weights. So that's our final feature vector. It has a feature function between the query and the entity, the type and the entity, the hints and the matchers. And there are pairwise correspondences in the score. So I won't go into the detail there. But that's the overall feature vector you get. So observe that the feature vector involves the query, the predicted type, the candidate entity, and the segmentation. Okay, and I'm going to score every such tuple. Before I get into how, let me jump ahead to what you see when you implement this. The lower curve here is the NDCG, which is the ranking performance you get. So as the rank goes here, you get more and more satisfied with the average answer. This is for a generic search engine which doesn't use a KG at all. That is where the query is gold labeled by humans with the canonical ID of the type which the user wants to see. So which scientist played the violin? The target type is scientist. Who discovered penicillin? Interesting. Who just says person? That's not good enough. A human would probably be able to restrict it further. More on that in a bit. So the generative model, directly coded, is significantly better than the lower bound. It fills about 28% of the gap between not using a knowledge graph and using a knowledge graph with human annotation on the query. And the discriminative model fills about 43% of the gap. So this was our first step. So generic, worse than generative, worse than discriminative, worse than human. So the next question is, we split the query earlier into target type and selectors. That is too coarse. The selectors can be further defined into other parts of the query. For example, if we say Dave Navarro first band, most humans would agree that Dave Navarro is the placeholder for E1, the entity that's already in the query. And T2 is probably a musical band. That itself takes a little bit of work to figure out that it's not a frequency band for radio waves, but it's a musical band. Right? Some people might argue that relationship. We don't know what role Dave Navarro played in the band. Right? But as a broad prior, as soon as the T2 is banned, chances are R is a participant, like the person was a performer in the band, rather than the manager or the owner or something like that. So this kind of shows that already the roles are not really disjoint, and we'll see more examples of that. Now, maybe in your knowledge graph, we have links between performers and their bands, but there is no record of the dates during which they performed in the band. We can fall back on the corpus to discover where they performed first. And so in this case, we would push first to be a selector. That's like a fall through where it doesn't match anything usefully in the knowledge graph. And there are more examples like that. So with this more complicated story, the selectors have now been further refined into queries in the entity, target types, which we already had, relation hints, and whatever still remains that we couldn't refine beyond selectors. So now this interpretation Z, which used to be just a two-way segmentation, will become a four-way segmentation. And that, of course, blows things up combinatorially. So there are many noisy interpretations. There could be overlapping labels. It's a little presumptuous to believe that our highest scoring segmentation is always the correct one. If you worked in the mode that we first interpret the query into a structured query and then we execute it on the logic graph, if your query is wrong, you lose it all. There's no recovery path. So what we will do is instead, we will do some sort of averaging over different interpretations of the query implicitly, and we'll see how. So here's a more complicated graphical model from the previous one. We start with an unknown latent segmentation Z, which may or may not be right, but a candidate E2, which is therefore observed. So this is gray, and that's all the others are white because they're latent and unknown. So the system is proposing a segmentation and proposing canonical IDs T2, R, E1, and S is not a canonical ID, but it's a bag of words which is left behind. What are the scoring mechanisms and the potentials corresponding to these nodes? So the first is that whatever the segmentation claims is a hint of the target type should be somehow consistent with the actual target type you're proposing. So if you say which scientist, one shouldn't pose T2 as cricketer. So this scores that consistency. Similarly, this potential scores the consistency between the claimed canonical relation involved in the query and some segment of the query which is a hint of that. So which scientist played the violin? Played is the segment part, and say person performed musical instrument, the canonical relation ID is there. And this scores the consistency. This is basically the score coming from an entity linker which finds that violin is the entity in the query. And finally, anything that's left over has some default potential for not joining one of the structured parts. In the lower part, we have to establish a belief that the candidate actually belongs to the type T2. If you take the knowledge graph as gospel, the whole truth and nothing but the truth, then that potential is just 0 or 1. But there is another rapidly growing area of research which talks about completing knowledge graphs. So knowledge graphs are incomplete, and we can probabilistically complete them using matrix factorization, using tensor factorization, using convolutional networks, all kinds of things. So that score can go in there. Knowledge graph did not tell me that an obscure John Smith was a cricketer playing for Manchester, but we have somehow discovered that is true with probability 0.7. So that score would go in there. Similarly, we get a score that E1 and E2 are connected through the given relation. So again, that's a score of the veracity of that relationship. And finally, from the corpus, we need to get some evidence in case all the other potentials fail us. The corpus gives us some evidence that the selectors are matching passages where E2 appears, ideally also with hints of R and E1, but those are slightly more optional. because R and E1 have already been covered in other parts of the query. The corpus doesn't need to support everything in the query. The corpus needs to support what's not supported through the KG parts. So in the implementation, we pay a heavy premium on the thick edges, which is that snippets have the entity E2 mentioned together with the words which fell through and was not interpreted as the other things in the query. Okay? And this is the scoring model. We can write out equation for learning the parameters of this model. But before that, I wanted to discuss very briefly these two, type hints and relation hints, and a little bit about the corpus scoring part. So type hints, basically, that part has to evaluate whether the type hint matches the claimed target canonical type. And we do this by creating a micro document for each type, using a whole bunch of techniques. And then from the micro documents, we make a smoothed Dirichlet language model and then we favor specific types over generic types. In the later part of the work, we did not use a language model from these word bags, but we simply trained convnets to recognize whether a target type appears in the query or not, and that performs much better. Same with relation language model. How are relation hints expressed in queries? And the objective is therefore to map relation mentions to KG relations. And we do it the same way. In the older system, we did it by bag of words and language models. In the new system, we used convolutional networks. There is, of course, a query corpus mismatch. The way the corpus expresses types and relations may not be the same as how queries express it. One example is you say, how fast does a bullet move? That's linear velocity, whereas if you say, how fast does an aeroplane's propeller turn? That's angular velocity, so the types are slightly different. But queries don't distinguish. And finally, how do we score corpus snippets? These are some of the features which we use. The number of snippets where the lexical distance between E1 and E2 mentions is less than K for various Ks, or the number of snippets with relation phrases between E1 and E2, things like that. Number of snippets where E2 appears and the fraction of query IDF which is covered is at least K. IDF is the rarity of the word in the query, roughly speaking. So before we get into how this works and compare it with the previous system, let me point out the limitations of query segmentation. There is, of course, a combinatorial explosion with the number of roles increasing. We started with only red and green words. Now we have red, blue, green, yellow words, so it gets more messy. And also the roles of query spans are not mutually exclusive. If I asked a query who discovered penicillin versus who discovered Antarctica, there's hardly any clue in who. Person as T2 is very non-selective, right? It's not very informative. And in fact, penicillin helps us infer T2 better than who, and even discovered. So the better paradigm, we eventually realized with many other groups, is that having chosen a query interpretation which consists of the bunch of E1s in the query, the proposed canonical R and the canonical T2 and the candidate E2, we extract features between these and the whole query in a way with a network architecture which I'll show in the next slide. And then we learn weights W to score these interpretations. So these particular features extracted from the interpretation. Interpretation, it's just a candidate answer. The structure of the query only depends on E1, R, and T2. And E2 is one instance. But we don't subscribe to that. We include E2 in our interpretation, and we score at a finer grain. Okay. If you only interpret the structured form of the query, then you ask it on the knowledge graph, and you extract a set of entities. Now you have to subscribe to a set-to-set comparison, the gold set, the system set. Whereas what we want to do is to score E2s directly as a ranking problem, not as a set extraction problem. So why is diffused clue an important notion? So coming back to our problem, you might say that if the query is baseball team World Series 1998, then both baseball team and World Series give you hints of T2 and not be forced to segment it. Similarly, E1 may actually include World Series and 1998. The relation, you might say, is lost. Right? And selectors, maybe 1998, maybe baseball, depends on what the corpus offers. So there should be flexibility to have a many-to-many assignment between the structural components and various spans in the query. And this is ideal for using a convnet, because if you sweep a convnet over the query 4 times, one for T2, once for E1, and so on, the different convnets will focus on different parts of the query, not necessarily disjointly, to match with whatever they're supposed to discover. And that leads to this architecture. So during training, we start with the query and the gold E2 star or set of gold entities. And the first thing we do is do the E1 linking. So you say, what's the height of Michael Jordan? Michael Jordan is linked to a knowledge graph. Once you do that, you can remove the occurrence of E1 from the query and you're left with everything else. E1 is sent to a knowledge graph and the corpus simultaneously. The corpus has been annotated with entities using an entity linker. So from there, we get candidate E2s from both the KG and the corpus. And now, since E2 can be located in the KG, we also get the proposed target type and the relation, which is connecting E1 and E2. Right? And the corpus also gives textual contexts in which E2 appears. Now we need to fit this together. So the first thing that happens is a convolutional network runs over the rest of the query, and it looks at the relation and says, okay, I think there's 0.9 consistency between the canonical relation proposed and the rest of the query. Another network matches the target type T2 with the rest of the query. A third network looks at each context and decides if that matches well with the rest of the query and has E2 in it. Okay. These corpus snippet scores are aggregated and then go into a score combination network along with relation matching and type matching, and that gives you the final score of E2. So 2 things to notice is that there is no uniform, single, simple network doing the entire job. Okay, that just doesn't work. Second is that this is meant for fault tolerance and resilience. If the corpus fails you, there's the knowledge graph. If the knowledge graph fails you, there's the corpus. Okay. Even if the knowledge graph exists and you can directly get to the target entity, scoring it may be improved substantially by using corpus support. So anytime there is synergy, we can exploit it. Anyway, once we get the score of E2, we can use it for ranking. And since we know E2 star, we can now evaluate all kinds of entity ranking losses. Or we can do set-oriented losses as well. Okay. So in the latest system, the language models in these 3 parts is replaced with 3 convolutional networks. And those are specialized to 3 subtasks of identifying R, T2, and passages with E2 and S. These are not trained end-to-end. And end-to-end training is sort of a fashion, and it doesn't necessarily hold in reality. I mean, none of us, natural intelligence is not end-to-end trained. We can read a news article about a railway accident where some number of people were injured and others were killed. And we can say, oh, the total number of people affected was injured plus killed. That addition we learn to do at a time when we are not really reading newspaper articles about accidents. So these examples were given by Dan Roth, and there's also another great example of image recognition with end-to-end training. So suppose you have a bunch of images, and each image has a line. The line has either positive slope or negative slope. It is trivial to train an MNIST-style network to output +1 for positive slope and -1 for negative slope. But suppose my entire learning problem is made different. I give you a pool of images with irregular size of pools. I can give you 10 images, I can give you 17 images. And what you have to label or output, the system has to label whether the parity of the number of lines with positive slope is odd or even. So it doesn't make sense to end-to-end train this. Think about it. Any end-to-end network will fail very badly on this. You need to actually first learn to identify slope and then identify parity and train them separately. So it's a little bit of a similar situation. I don't want a single network to try to specialize to 3 tasks. I want to keep them separate and then combine them in a final network. This is also good for interpretability. It helped us a lot while we tried to debug why some part of the system was not working and fix it. So there is this problem that this entire thing is distance supervised. The labeled instances are just queries and gold entities, and not the actual interpretation of the query. Interpretations are very difficult to collect, so you don't do that. So there are 2 approaches based on what you regard as an interpretation. Either E2 is not in the interpretation, in which case that gives you a template of a structured query, which you execute on the knowledge graph to give you a bunch of E2s. You compare E2 with the E2 star, and that gives you a set-oriented reward, recall precision F1. Or you keep E2 in this triple, or tuple. You jointly interpret and rank the E2s, as in the previous picture, the last thing here. And then you get a ranking loss. The ranking loss may be area under the curve, mean average precision, or NDCG. And that can be used to do backprop into these networks. Now, how does that work? A good or relevant E2 should beat a bad or irrelevant E2. But what is good or bad? The score is determined under the best interpretation for each. Now that creates a problem. The right-hand side max is fine, but the left-hand side max leads to a non-convex feasible region. And to handle that, we replace the left-hand side maximum with a convex combination. And this looks a bit hideous, but there's nothing in it. So U is the convex combination. We alternately fit the weight of the model, and we squeeze down the entropy of the U distribution. This is non-convex, but don't panic. It works out fine. And we call this the latent variable discriminative learning paradigm, where the constraints have latent variables which we quantify over. Okay. This can be solved by alternately invoking a linear program and a maxent classifier, basically. That can be shown. So coming to experiments, there are 2 data sets which we turned into 4. There are years of question answering data sets in Trek and INEX. They are usually provided as long natural language queries, which are syntax rich. We had volunteers turn them into telegraphic or syntax poor queries, with the requirement that Google had to list the answer in some page in the top 10. Web Questions is a data set from Stanford in 2013-14, which was explicitly designed so that 100% of their queries are answerable by the KG alone. They wanted to do research in semantic interpretation or question compilation. They wanted to turn the string query into a structured graph query and execute it on the knowledge graph to get a set-valued answer. Web Questions was also given in full, well-formed natural language, and again, we turned a fraction of that into telegraphic query form. So number 1 and number 3 are syntax poor keyword queries, KW. Number 2 and number 4 are NLQ or natural language queries. As we shall see, many existing techniques fail quite badly once you give them telegraphic queries, because they depend a lot on linguistic clues in their front end, and we don't. Also, in contrast to Web Questions, only 57% of Trek INEX can be directly answerable by the KG. So the corpus is vital for additional evidence. And we'll see that concretely. So we have a broad spectrum of query syntax support. We have a broad spectrum of what is covered by the KG and what's not covered. The first thing I want to show is that KG corpus synergy is critical. In both cases, we see that using both the KG and corpus is far better than using only the KG or only the corpus. Because Web Questions was designed so that the knowledge graph can answer everything, KG on its own is better than corpus on its own. In case of Trek INEX, corpus on its own is better than KG on its own. But in both cases, both is best. The other question which I promised to answer some time back is, we had this very simple model of type plus selector, the red and green. Has it been worthwhile refining it to have these 4 kinds of segments? And the answer is again yes. The type plus selector would give you something better than no interpretation or no KG, but those are improved substantially by the 4-way segmentation of the query. But this still doesn't have the neural system listed here. So the type plus selector is just find an entity near some selectors. So this shows you, so this Joshi plus is basically the better of the green and yellow in general. So this shows you how Joshi plus compares to our latest neural system. And there again, we take huge leaps in map, MRR, and ADCG by having the 3 conv nets with a trainable combination network at the end. Observe that on this NLQ questions, we only have the latest system AccuScience, and we don't even have Joshi plus, because the queries were too long for Joshi plus to search over all possible 4-way segmentations. How do we do in terms of set retrieval, which is where other people often benchmark their system? So this has other competing groups work. Accu is the system written by Hausman and Bast in 2015. This is the Stanford 2nd generation paper. Now, as you can see, in 3 of the 4 situations, this is case 1, 2, 3, and then 4 has a lot more people entering the fight. AccuScience has 2 entries. One is, we're trying to compare a ranking system with set retrieval system. Other people have written set retrieval systems. We have written an E2 ranking system. So to make it a set, you have to cut it off somewhere. So the one where you say threshold is a very simple network which uses the scores to decide where to cut it off to get a set. And then you get an F1 score. But we don't want to mix up how good our ranking system is with how good our cutoff system is. So we evaluate them separately. In other words, we also say if we took our ranking system and could perfect the place where we want to cut off, with hindsight, where would we cut it off to get the best F1? That gives you some upper bound of what F1 we can reach. So in all these cases, even our non-clairvoyant threshold beats all the other existing work. And this case is the one that prior research has most polished their systems on. Here we are kind of in a funny place. We are 3rd compared to the F1 other people get with semantic interpretation, set retrieval. But with ideal threshold, we'd go far beyond them. So we are working on how we can boost this to somewhere between 50 and 62. Hopefully we'll go past those numbers. So this is what has happened, and this is where the future is. If you go to search engines and say Manuel Blum Sun College, both prominent search engines will do quite well on this because it represents taking 1 hop per word on the knowledge graph. Locate Manuel Blum, walk on the edge for Sun, go to Avrim Blum, walk on the edge college and see that he graduated from MIT or he teaches at CME. But if you ask, college where Manuel Blum's relative teaches, not so well. Try it out. You'll probably locate the answer somewhere in the text of the first 1 or 2 pages, but again, there's no call out. If you ask, movie directed by Bernard Chazel's relative, and remember, I mean, there are very, very smart people working on this, so this changes by the hour. These examples were collected a few weeks back, and things may have changed by now. What you'd like to do, if a search engine was sufficiently cooperative, a sophisticated user is okay, perhaps breaking up this query into Bernard Chazel related to R directed M is a movie, and I'm looking for M. Right? Or if I want to ask about companies that make fanless motherboards, I might want to break it down helpfully into M is a motherboard, M has attribute fanless, and C makes M, and C is my target. So as we are going down this list, it's getting progressively harder, and existing search engines are doing worse and worse in general. Cities where Einstein taught is a deceptively simple one, because people don't teach cities. People teach in universities which are located in cities, and there's this implicit 2-hop query, which is very short. So you'd like to say Einstein taught at U and U located in C. Okay. What I'd like to do is to build a query system not for end users, but for experimenters to see if I broke down a complex query manually into pieces, each of which is almost a single relation piece, how well can we join this from multiple evidences in the corpus and KG and give you good rankings for the bold target? Okay. Things get progressively much harder. Satyajit Ray age when Sukumar Ray died. So you compile that to Satyajit Ray born in Y1, Sukumar died in Y2, report Y2 minus Y1. Okay. And then things which are pretty much out of reach. Countries that have more rivers than India. So how do you compile this manually? Now you have to really start SQL writing, right? So R is a river, C is a country, R located in C, build a table or a view, subquery, R, count C, group by R for India, for all other countries, compare, right? So it's a very simple keyword query, countries that have more rivers than India. And you could think of e-commerce users wanting to ask these things. I mean, phones which have more SIM slots than Redmi 5. Or phones whose batteries last more than Galaxy 7S. Right. So it should be possible to do this. And there's been work on this. How am I doing for time? Okay. So the rest will be a little bit of a blur. I apologize for that, but work has been happening on this front too. So there was a paper in 2016 from Berkeley, which had an inventory of modules with elementary operators. Find something, look up something, relate something, and make a conjunct of sets. So each of these modules was represented as a continuous small neural network. And the whole point was, can the system learn to build a neural network, not have a fixed network and learn its parameters? For every query, I need to stitch together the neural modules in a different configuration. Right? So that was the layout. Choose a layout Z. That's the operator graph layout, which when I execute, I should get Y, the answer. So what cities are in Georgia? The correct network layout is look up Georgia, relate by the relationship in, or containment, also find all cities, and then intersect it as an AND. So can I learn how to do this? Now there are two parts to this. One is the network which chooses the network, that is theta L. That part is really messy and difficult. The other part, once you make a layout, how am I going to tune the parameters inside the modules to give the correct answer? That's not so difficult. That's relatively easy. But this difficult and messy part of going from a token sequence into a network layout, there was a later attempt improving on this from Google, which tried to choose a layout using a memory network-based sequence-to-sequence model. So the input query is a sequence of tokens. The output is a program. A program is a sequence of actions. Each action applies an operator to a bunch of arguments and stores the result in a variable. And a program is a sequence of these. For example, largest city in the US would first look up US as an entity from the knowledge graph, would store it in a variable V0. Then, the second would be an operator, which would be invoked on V0 with a hop called city in. This would be stored in the variable V1. Okay? And then, there would be this argmax on population, which would be stored in V2, and that's the output. So this is a sequence of program lines which come out. So the sequence-to-sequence translator has memory. The encoder reads the query X token by token to the end and outputs the final state to the decoder. The decoder outputs the program token by token, consulting all the encoder states as in standard attention models. Both the encoder and decoder may update memory. Okay. Later arguments can, of course, refer to earlier Vs. How to choose that is tricky and interesting. And the big challenge is that the reward is completely deferred. Once the full program is output, you run the program on the KG. And if you got a good result, then you give the reward to the translation system. So managing that kind of deferred reward is very tricky, and they did not do that great a job. The framework is nice, but there are many details in managing the reward process. So here's another small picture to show what happens. That's just for completeness. It doesn't really matter in the explanation. So first, the encoder LSTM looks at the whole query, largest city in the US. And whenever it can ground something like E1, it registers the E1 with a variable encoding and a value encoding in a memory network. And then the decoding starts. Every step of the decoding emits something like hop R1 city in, and then bracket argmax R2 population, and so on. So how does the decoder know that I have to look up R1? What happens is, at this point, the internal state of the LSTM will start looking like V1, and then I will look up the value and get R1, and that's why I'll emit R1. So it's a little bit of a souped-up LSTM which consults the memory to decide if it wants to emit a variable name or not, or which variable name. When there are multiple variables, later stages have to decide that at this point you want to emit R2 and not R1. That's also part of the decoder work. So it looks up something close to V1 to generate the memory address R1. Now observe that the decoding process itself is part of the backpropagation, but the reward can only be achieved if you execute the program on the KG, which is not backpropagable. That's a discrete space. That's not smoothed out. So the magic of LSTM is supposed to solve some things for you. We said which city, therefore I emit the hop with a city attribute, or I saw largest, and that led to triggering this argmax and population later on. In some cases, largest means population. In some cases, it means area. Hopefully, my training data will teach the system to do all this. So there are many, many details here, and it's not. So if you look at some of the queries in the examples I gave, this architecture will probably work okay for about half of them, not the lower half, because the reward is too distant. So we're working on ways to improve that. So in conclusion, question answering should definitely, in the wild, open question answering should use both KG and Corpus. And they both have their strengths and weaknesses. The other important thing is that the network that gave us the best answer was extremely tailored and heterogeneous. It was not one of these MNIST or the other deep image analysis networks, or not like a very uniform structure LSTM or RNN. It's not like that. And the heterogeneity really mattered. Query understanding is improving, but it's still brittle. And what we are after is like this schema-light, syntax-agnostic evidence aggregation. We're not going to commit on a specific interpretation of the query. We're going to fuzzily sort of do a Bayesian integration over all possible interpretation and just rank the E2s. And decomposing complex queries into subtasks and assembling the answer using arithmetic and logic and set operators is still a major challenge. We have some other related work. Last year we did some work on neural comparison of short passages using LSTM and then earth-mover distance on the states, followed by ordinal regression. That seems to work pretty well. So another interesting paper we did is on named entity disambiguation. Suppose you learn to disambiguate between Jordan the river and Jordan a person. You have somehow learned something about distinguishing geographical things from people, and that should be helping you disambiguate between Sydney the city and Sydney a person. So existing neural entity disambiguators don't really use this synergy, and we have a new network architecture to do this as multi-task learning. We have this recent work on neural representation of partial orders, where entities are points, but types are cones or rectangles. And we can judge how well an entity fits into a type, or whether a type is a subtype of another type, based on incomplete training data. And also, if you don't have supervision about what is a type, we only want to regard a type as a noisy shorthand for relations an entity can participate. And we have an ACL paper which enables us to do knowledge base completion by modeling types without any explicit type supervision. So it's like an unsupervised type system which magically learns to predict symbolic types pretty well as a verification mechanism. And then there's some work on combining signals from two paradigms of knowledge-based inference. One is matrix factorization, other is tensor factorization. And if you combine them, you get state-of-the-art results in knowledge-based inference. So that gives you a vignette of things that interest me and my group. I'd be happy to take questions.
If you have a question, please raise your hand and we'll get the mic to you.
Mine is a bit open-ended. You're talking about web search, knowledge graphs, and corpus. In the e-commerce world, is it very naive to equate a catalog with something like a knowledge graph and maybe product descriptions and reviews for a corpus? Maybe the techniques could become a bit simpler. So do you see potential for?
So as we have been discussing, I think the catalog gives you major chunks of what you might call a knowledge graph. But some things are kind of missing. Those are the common sense items. So you use a drill for drilling a hole in concrete or wood. Right? No one states that in the catalog, that, oh, you can use this drilling machine to make furniture. Right? So that general knowledge might come from a generic knowledge graph, whereas the catalog provides more specifications or user experiences, which may not be out there on the public web as much. So blending these two properly might get you further than just the e-commerce catalog.
Same applies for a web corpus versus product description from a seller.
So descriptions are necessarily biased as well, right? When you say what's the typical battery life of an iPhone, you do not want Apple's version of it. You want the user's version of it.
How about reviews?
Yes. So, but reviews are also curated and not necessarily in the wild. Right. Other questions? Thank you very
Big
much.
round of applause to Professor Soumen for being a part of our Blue Sky Talk series. Before we wrap up this event, we ran a quiz contest, and I'd like Chalaya to take you through the answers and announce the winner. If you're here, please come up front. We have a small goodie for you.
Yeah, Professor will be here for some more time, so if you want to ask him informally some questions, you will. Where are the answers? Yeah, I got it. Today, I'll just tell the winner. Yeah. So we don't have questions and answers up front. How many of you participate in the quiz? I'll try to embarrass the audience. So maybe then she will send answers in a separate mail. Is Rashmi here? Rashmi Gulane? So she's not here, so you have to connect with her offline. So the intent was, I think Professor was showcasing a lot of papers. So before each talk, we tried to give some papers. Maybe it was easy for me to take the answers out. I know that you had to do a lot more work because, but I really appreciate the time you spent on that. It improves the engagement. It will probably spread the culture also for the problems we are trying to solve. Maybe some work has been done in the academic literature, and you should feel free to go and leverage that. That's the intent. So thanks a lot. So are you going to thank the?
Let's hear it one more time for Professor Soumen. A big round of applause. Thank you for being a part of our Blue Sky Talk. As Chalaya mentioned, if you'd like to catch up with Professor, he's here for a bit. Thanks to each and every one of you for being a part of this talk series. See you next time. And we have some snack boxes at the back, so help yourselves. Have a nice day.